Hello dear IIT JAM BT aspirants. I welcome to Chandu Biology Classes. I hope you are using these PCM series very effectively for your upcoming IIT JAM BT exam right now. So here you can see this is our third session on thermodynamics topic right now. So in this chapter I am going to cover like all the important topics by looking at the previous year questions from this IIT JAM BT from past 10-15 years of questions. Okay, so I already finished this states of matter, gaseous states of matter. So if you haven't watched it, yes, you can go through the live sessions of this channel. You can find all the sessions that I have taken on this PCM series for IIT JAM BT. Okay, so now look at these questions. First of all, see, all these questions are from these states of matter, that is gaseous state. So from 2017 and this is from 2024, all these questions were discussed okay in the previous years previous sessions. You just try to answer them. If you are facing difficulty to answer, you just go and watch those live sessions that I have made previously. Okay, right. So again, this is one of the very important topic, that equipartition theorem. Okay, so where we have most of the questions from this thermodynamics or from this gaseous states or from this equipartition theorem only. Okay, so try to learn this topic very effectively. Anyways, I am going to solve few questions related to this equipartition theory. Okay, in this thermodynamics topic also there are some questions connected here also. Okay, let me cover those here also, because in the last session also I covered this. Now here also I am going to cover the same. Okay, see, if you want, you can try this. If you are facing difficulty to answer, you can watch the previous live session. Okay, right. So today we will be discussing few important things. See, in the last class where I have discussed about, let me check, is there anything missing here? Okay. Yes, I hope it's clear now. Yeah. Yeah, just tell me which of the following reactions are having delta H equals to delta U. Very simple. If you are from class 12th chemistry background, then you can easily answer this kind of questions, because these topics were already discussed in the class 12th itself. Okay, so let me connect you to this topic once again. See, I have discussed in the last class that delta H is equals to delta U plus delta PV. Okay, so here P and V represents pressure and volume. Okay, for an ideal gas we can take PV equals to nRT right now. So now you can write delta H will be equals to delta U plus delta nRT. Since we are talking about gas, I am indicating this is Ng. Okay, right. You can write this as delta U is equals to delta U plus delta Ng RT. Okay, right. So what is this delta Ng indicates here? See, this delta Ng is nothing but just it's a difference of number of gaseous products minus number of gaseous reactants. So just take it like summation of n gaseous products minus n gaseous reactants. Okay, so how many gaseous products are there? 2. And gaseous reactants are how many? See, N2O2 are also gases now. Yes, so 1 and 1. So total how much it is? 2 minus 2. This is 0. If this delta Ng, see, 2 minus 2 is 0 for this reaction. If this is 0, this whole term becomes 0 now. Therefore delta H is equals to delta U. It means this will be applicable, or which this will be satisfied by first option, and let us confirm with the second option. See, here we have stoichiometric coefficient 1, CO, carbon monoxide gas only now. Yes, you need to consider only gases. Okay, here half O2, yes, this is also gas, but here carbon is there. Carbon is in solid form like graphite form right now, so which is solid substance. So it's having coefficient 1, no need of considering this because it's a gaseous substance, solid substance. So you can take this delta Ng for second reaction. You can take gaseous products are 1 and gaseous reactants are 1/2. It means simply you can write delta Ng is 1 by 2. Okay, therefore yeah guys, just hold on for few minutes, there is some technical issue, we'll come back again. Yes guys, I hope, now it's visible properly. Now tell me what I told you. So just find delta Ng value. If delta Ng value is 0, then you can say delta H will be equals to delta U, because delta Ng RT we are writing now. If this term becoming 0, then this second term completely becomes 0, therefore delta H will be equals to delta U. So just find delta Ng values by looking at here. See, if number of gaseous products and number of gaseous reactions are equal, then it will be 0. But in this case, if you see, only one carbon monoxide is there, which is a gas at product side, and this is half O2 is there. It means delta Ng is not equals to 0, it is 1 by 2 now. So in this case, in this second case, delta H will be equals to delta U plus 1 by 2 RT. Okay, in which case? In second option case. In third option case, if you observe, so we have one product, one gaseous product, one gaseous reactant, okay, and see, is this balanced? No. So you just take this as O2 like this, then it will be equal. Okay, so by looking like that, so whether it is, if it is gaseous, like O2 is a gaseous species, na, C plus O2 gives rise to CO2, it is given. So we have one CO2. If you find delta Ng, then it will be one gaseous product and one gaseous reactant, then delta Ng is equals to 0. Because carbon I am not considering, because it is exists in its stable form, that is graphite form, which is a solid substance right now. Okay, so you need to know the standard states, whether carbon exists in which state, physical state, what is its gas, like physical state, gas, liquid or solid. Okay, right, like that if you know, then you can substitute in this formula, you can calculate delta Ng. If it is 0, then delta H is equals to delta U. So as per this question, I can say first option is correct as well as third option is also correct. Okay, because as per this question which I am showing on the screen, because it is also equal, like number of gaseous product and reactants are same. And when it comes to this fourth option, you can see one gaseous product and 3 by 2, like 1 into like this one is there, and here we have, this is unequal, delta Ng is not equal in this case, not equals to 0 in this case, so it is not equal. So you can say 1 and 3 are the perfect answers for this particular question. Okay, and then next, look at this. If the heat is supplied to an ideal gas, look, this is very easy. If a heat is supplied to an ideal gas in an isothermal process, what happens? Out of these 4 options, you can choose one option that is perfect here. See, if I am drawing a system here, consider this is a system where we are supplying some heat. What they are saying, if heat is supplied to an ideal gas. See, in this system what we have, ideal gas is there. What is there? Ideal gas is there. To that I am supplying heat, plus Q amount of heat I am supplying. So under isothermal process, so what happens? The gas will do positive work, the internal energy of gas will increase, the gas will do negative work, and the said process is not possible. See, it is very easy. Yeah, it is very easy. Look at this. We know from first law of thermodynamics, delta U is equals to dq plus dw, or del U plus del W we can write right now. So they have mentioned here, this is happening in isothermal process. If it is isothermal process, what happens? Isothermal process means T constant right now. If T is constant, then change in temperature will be, temperature is constant, then change in temperature will be 0. If this is 0, see, the internal energy U is directly proportional to temperature. U is directly proportional to temperature. That internal energy of a system is directly proportional to temperature. If temperature is constant, so internal energy also remains constant, remains the same now. Therefore, change in internal energy du or del U will be also equals to 0. Here del U also becomes 0. This term is becoming 0 for isothermal process. Very, very important that du for isothermal process, internal energy change for an isothermal process will be 0. You can remember this. Okay, and the next thing what you need to remember here is, if this is 0, then we can write dq plus dw equals to 0, which is equals to, I can write dq is equals to minus dw. It means whatever the heat you are supplying, whatever the heat you are supplying to the system, that will be utilized for doing work. So it means work done by the system. It means what you can say, the gas will do negative work. Yes, see here negative symbol is there now. It means negative work means what? The system will be doing work here. It means the work done by the system, that should be indicated with a negative sign, or you can say negative work. So here you can say third option will be perfect answer. The same question if I ask in different manner, see I am writing this is a system which is having ideal gas. Okay, now some Q amount of heat is released from the system. What I am saying, Q amount of heat is released from the system. It means some amount, Q amount is released. I can say negative heat. Okay, and if it is Q amount of heat is releasing, then what should happen for an isothermal process? See, if work is done on the system, then Q amount of heat will be released. So if Q is positive, W should be negative, or in the vice versa, like or in the reverse manner, you can remember. Okay, so I hope the concept is clear. If they modify the question, if they ask in the upcoming exam also, I hope you can able to answer this right now. Right. Okay, next. Next, look at this question. Can you try to answer this? So you can just try to answer that question. What is your answer for this? The following data are given. See, these are the 3-step reactions are given, and they are saying the net change for the reaction. See, these are the 3 reactions are given. Using these 3 reaction, we need to say what is the net heat change for this final reaction which they have mentioned. Here I am writing N2 plus O2 gives rise to 2NO, they are saying right now. So for this reaction, what is a heat change? Delta H. Okay, so delta H final, you can say delta H final will be equals to how much? By looking at this H1, H2 and H3, we need to answer this. Very simple. So this is called Hess law. Okay, it's an application of Hess law. So what it is saying, see N2 here in the reactant side, yes, first reaction, and the next O2, where do we have O2? Yes. Where do we have O2? Yes, here we have O2. It means reaction 1 plus reaction 3, reaction 1 plus reaction 2 you can take, reaction 1 plus reaction 2, and the next, see here we have 3 water for the reaction 2 and here only 1 water. So it means what I should do, I should multiply this equation with 3, therefore it becomes 3H2O, we can take in that way, and the next we can reverse this reaction. So therefore this H2O and this second reaction H2O can be cancelled out. So simply you can say minus 3 by 2 delta H3, that's it. Okay, that's it. I hope, see simple, I will tell you using one simple example. See, plus O2, half O2 gives rise to CO. Okay, for this process I am saying delta heat energy change is delta H1. Now second step, what I am saying, CO plus half O2 gives rise to CO2. I am saying this as delta H2. Again I am writing a third reaction like C plus O2 gives rise to CO2. This is delta H3. Okay. Now what is the relation between this delta H3, H2 and H1? Simple. See, delta H3 will be equals to, it's nothing but delta H1 plus H1 reaction and H2. See, reaction 1 plus reaction 2 gives this reaction 3 right now, because reactant side CO, product side CO I can cancel. Therefore C as it is, half O2 plus half O2 become 1 O2 right now. Okay, so 1 O2, and this one is cancelled, we have product side CO2, that's it. Delta H3 will be equals to delta H1 plus delta H2, that's it. Okay, so this is the way to answer the question. Okay, in the same manner you just try this multi-step reaction we have. Look at the reactions, rewrite them in your notes and try to cancel out and try to make a final equation in this manner. So for making this equation, how you are modifying these 3 reaction equations, that's it. Either you are multiplying with 3 or dividing with 2 or you are reversing the reaction. So what you are doing, you need to look into it and you need to choose the perfect answer here. That's it. Very easy. You can try and tell me if you have any concerns with that. Okay, next. See, we have got a relation that enthalpy is equals to internal energy, that is E or U plus PV right now. So I can write dH is equals to dE plus dPV. In place of PV I can write RT also for 1 mole of an ideal gas right now. So dH will be equals to, see, this is very important relation. I am going to show you that few questions on this. Delta H equals to delta E plus R dt I can write, because R is a constant. In the place of PV I can write RT, where R is a constant I am writing outside. So D into T, so dt I am writing. Okay, so divide this equation with dt, therefore dH by dt is equals to dE by dt plus R right now. So this is what the relation we got. So from this we are going to get a new term here, dH by dt minus dE by dt is equals to R we got now, right. So now look at this, there is a term called heat capacity. What I am saying? Heat capacity. So what is heat capacity? The amount of heat required, amount of heat required to rise the temperature of a substance by 1 degree Celsius or 1 Kelvin temperature is called its heat capacity. It means the amount of heat required to rise the temperature by 1 degree Celsius or 1 Kelvin temperature for a particular substance. So it is nothing but heat I can represent with Q and temperature change will be dt. So amount of heat, the temperature raised will be proportional to the amount of heat or Q supplied to the system, heat supplied to the system or that particular substance. Okay, so I can write this Q is equals to C dt I am writing, or delta T. See here D or delta, here you can consider them as similar terms here. Okay, now this is C, whatever I have written, it is called as heat capacity. Okay, heat capacity. I will show you a few questions on this heat capacity. So just try to remember this, C is equals to Q by dt, or for small changes you can also write it as dQ by dt. Okay, and if I say this heat capacity for 1 gram of a substance, you should call it as specific heat capacity. If you are saying this for 1 mole of a substance, you should call it as molar heat capacity. Okay, what is specific heat capacity? Heat capacity expressed for 1 gram of a substance, and molar heat capacity means heat capacity expressed for 1 mole of a substance. Okay, now heat capacity can also be expressed at a constant volume. If you are expressing this at constant volume, it means what? Heat content of the system that is at constant value by change in temperature, and we are measuring it for 1 mole of the substance. So I can say this CV as molar heat capacity at constant volume, So this QV is nothing but I can write it as du. Why I am writing du? Because QV is nothing but heat content of the system measured at constant volume, that is nothing but internal energy change, or du. Okay, I can write du by dt. In the similar manner, if we calculate the heat capacity, molar heat capacity at constant pressure, I should call it as Qp dQp by dt I am writing. So dQp means what? heat content of the system measured at constant pressure, which I can indicate with dH. So dH by dt, that is equals to Cp. So look at this thing here, dH by dt means I can write Cp, and dE by dt means I can write Cv, which is equals to R. This is for 1 mole of a substance, 1 mole of an ideal gas. For n moles you can write Cp minus Cv equals to nR. You can write in this manner. Okay, hope this is clear. The final conclusion is what? Cp minus Cv equals to R, you can remember. Okay, this is the final conclusion you should remember from this derivation. Okay, right. Now from this derivation, like what we got, Cp minus Cv equals to R we got now. So now what I am doing is I am dividing this equation with Cv. So divide Cv, Cv, and here also Cv. See, Cv by Cv means 1 I can write here. Cp by Cv means I am introducing a new term called here Poisson's ratio, indicated with gamma. So what is gamma? It's called Poisson's ratio, which is nothing but Cp by Cv. So I can write gamma minus 1 is equals to R by Cv. Okay, from this Cv will be R by gamma minus 1. Okay, right. So what is this gamma here? What is this gamma here? See, gamma is nothing but Cp by Cv I am saying. So now in the exam you will be seeing this kind of questions. Let me show you. For monoatomic gas, what is the Cv value? What is Cv value? Direct question you can expect. What is the value of Cv? And what is the value of Cp for monoatomic gas? And what is the value of gamma for monoatomic gas? These are the simple questions you can expect. Let me tell you how can you calculate this. See, Cv means what we have written? Cv means du by dt we have written right now. So internal energy of a system is directly proportional to temperature we know. Right now it is directly proportional to temperature, right? And one more thing, so this U can be calculated by using its translational degrees of freedom, and rotational degrees of freedom, and vibrational degrees of freedom for a particular substance. How this translational, rotational, vibrational degrees of freedom will be there? See, every species, every atom or molecule you are considering, it will be having some energy internally that will be associated with the number of translational vibrations or rotations that a molecule can freely do. Okay, see, everything you are taking, any atom you take or any substance you take, there will be some energy internally associated with that molecule right now. So for that molecule, that energy comes from its translational degrees of freedom or vibrational degrees of freedom or rotational degrees of freedom. Okay, so it means degrees of freedom means the number of independent ways it can like translate. I can say that as translational degrees of freedom. Okay, or rotational means number of independent ways it can rotate. Okay, so now for any substance there will be 3 translational degrees of freedom. What I am saying, for any substance there will be 3 translational degrees of freedom. So it is nothing but x axis, y axis, z axis are there now. You just remember along each coordinate axis there will be 1 degree of translational degree of freedom we have. So for each translational degree of freedom there will be some energy associated with that is considered as half RT. Okay, half RT is the energy associated with each translational degree of freedom. So like that, how many translations can be possible? 1, 2, 3 are there now. So total translational degrees of freedom will be 3 by 2 RT. Okay, and in this way we have rotational degrees of freedom and vibrational degrees of freedom. See, vibrational degrees of freedom is activates at higher temperatures. So at normal temperature we have only one is the translational degrees of freedom and rotational degrees of freedom. So for diatomic molecules, see, molecules can be linear and non-linear now. So for linear molecules, I am saying for linear molecules, number of rotational degrees of freedom will be equals to 3n minus, see, number of rotational degrees of freedom are just 2 you can say. And for non-linear molecule, for non-linear molecules, rotational degrees of freedom will be 3. That's it. You just remember this thing, and if they ask you to find vibrational degrees of freedom, you just use the formula as, see, total degrees of freedom will be 3n. How much I am saying? Total degrees of freedom will be 3n. So out of this 3n, translational degrees of freedom are how many? Just I am saying 3 translational degrees of freedom. For linear molecule, rotational degrees of freedom are how many? 2. So you can say 3n minus 5. Okay, it's very simple. With 1 or 2 questions you can easily solve this kind of question. Just hold on for few more minutes. I will give you clear cut explanation using 1-2 examples. And this is for linear. And for non-linear you can write 3n minus 6. So what is this? N represents number of atoms. Okay, number of atoms. See, simply I am taking here a monoatomic gas like helium gas I am taking. Okay, this is monoatomic gas example. Monoatomic. And the next CO2 I am taking, which is polyatomic, but it is linear right now. And I am taking third example, polyatomic, non-linear. That's it. So look at this helium gas. It's monoatomic gas. Now for monoatomic gas, like monoatomic particles, there is only translational degrees of freedom. No rotational, and no vibrational. Only translational degrees of freedom. Therefore, total degrees of freedom will be equals to translational degrees of freedom only. So they are how many? 3. So 3, each degree of each coordinate axis will be having of 1/2 RT. Therefore, total energy for this monoatomic gas is just 3/2. So now what is its energy? I can say internal energy will be equals to 3/2 RT. That's it. This is the internal energy. Okay, which is coming from its translational degrees of freedom. But there is no vibrational, rotational degrees of freedom for monoatomic gas. You can remember. Okay, if there is any blur, please mention in the chat box so that I will remove out or I'll sort it out as soon as possible. So now see, this is the energy now. So from this we can calculate CV. So CV, how can we calculate? See, we got CV equals to du by dt right now. So it means we can say d by dt of 3/2 RT. Okay, so it means this becomes 3/2 R. This will be the CV value. Similarly, if I ask for CP, what could be your answer? CP will be no. How can you say? CP minus CV equals to R. Therefore, CP will be R plus CV right now. So R plus CV, that is R plus 3/2 R, that is 5/2 R will be your CP. Okay. Now if I ask you what is the Poisson's ratio for this monoatomic gas, simply you take gamma will be equals to CP by CV right now, that is 5/2 R and 3/2 R. So R 2 cancel, so this is 5/3. So you can simply write it as 1.66. What is the Poisson's ratio for monoatomic gas? It is 1.66. Similarly, you can do it for polyatomic gases, like linear if it is, so it has translational degrees of freedom and rotational degrees of freedom. Okay, at high temperature we can have vibrational degrees of freedom. So translational degrees of freedom, energy associated with translational degrees of freedom is 3/2 RT, and energy associated with the rotational degrees of freedom is 2/2 RT, that is simply RT. So there are two rotational degrees of freedom for polyatomic linear, and for this 3 rotational degrees of freedom for polyatomic non-linear. So each rotational degrees of freedom is associated with 1 by 2 RT. So therefore it will be 3 by 2 plus 1 RT you can write. So this will become how much? So this will become 4. This is C. Simply I can write 2 by 2 now. So you can write it as 5 by 2 RT. Okay. So that's it. Okay. So this will be the U. Therefore CV becomes how much? This is CV becomes 5 by 2 R. Again CP becomes how much? CP becomes how much? R plus 5 by 2 R, that is 7 by 2 R. By 2 R. And now CP by CV becomes how much? CP by CV will be just a ratio of 7 by 2 by 5 by 2, that is 7 by 2 by 5 by 2 means 7 by 5 will be remaining. Therefore this will be 1 point around 1.4. Okay, it's 1.4. And if you similarly if you calculate for this, you can write 3 by 2 RT translational plus vibrational will be at high temperature only, rotational will be 3 by 2 RT. That's it. So you can say 6 by 2 RT, this is U, that is 3 RT, this is U, and CV becomes 3R, and CP becomes R plus 3R, that is 4R. And if I ask for CP by CV, that is gamma value 4 by 3, that is 1.33. So why I am giving you these values? Yes, these are highly helpful when we are solving the questions. Okay, so this is a concept that you need to know. Just make it a note of it, then you can able to solve easily any questions related to this type of explanation. See, again whatever I have discussed, it is everything is mentioned here. You can take a screenshot of it for further reference. Okay, let me show you some simple questions. See here what they are saying. Is it visible or not? Five moles of ideal gas having Cp values given, heated, then find the delta H. So delta H is nothing but N. See, just now I told you Cp equals to dH by dt. Right now from this I want dH, then I can write Cp dt. This is for 1 mole. If it is for n moles, NCp dt. So I can use this equation here. Delta H is equals to N is how many moles? 5 moles, and Cp is how much? 7 by 2 R. Okay, multiplied with dt. How much temperature difference? 87 minus 27. So it will be 0 and 6. Okay, 60 is the temperature difference. dt is 60. Therefore they are saying R, they want answer in terms of, see, they want answer in terms of either calories or in joules. Let us calculate in calories first. R can be taken as 2 calorie per Kelvin per mole. Okay, so just substitute here 5 into 7 by 2 into 2 calorie per Kelvin per mole into 60. So 2 can be cancelled. So therefore it becomes how much? It becomes how much? This will be 6 5s are 30. So 30 into 7, 21. See, this will be 300 into 7, that I can write 2100. Okay, so where do we have 2100 calories? Yes, so second option will be perfect answer for the question. Hope whatever the steps we have followed during this are clear, very easy right now. So in the same way, what if they ask CV by giving the same data, or they ask du, how can you calculate this? If they ask for du, simple, they have given Cp now, from that you can find Cv by using Cp minus Cv relation. Okay, after finding Cv, just substitute over here, therefore you will get your du. Okay, so du equals to n Cv dt, the formula that you need to use here. See, look at this question. 1 mole of an ideal gas expanded isothermally from initial volume 1 liter to final volume 10 liters. Then what is the internal energy change? See, you need to know some isothermal process, adiabatic process, what exactly this thermodynamic processes are. See, I have given some basic idea in the previous class also. See, when I say isothermal process, it means temperature is constant. What is constant? Temperature is constant. Therefore, change in temperature will be 0 right now. So, here what will be the work done or what will be the internal energy change, they will ask. Simply you can write from the first law of thermodynamics, du, internal energy change is equals to dq plus dw right now. So, since temperature is constant, its internal energy change also, internal energy also remains constant, therefore its change du will become equals to 0. If du is 0, then you can write dq equals to minus dw. It means whatever the heat you are supplying to the system, that will be completely utilized for doing the work only. So, if you supply the heat, if the heat is absorbed by the system, that complete heat is utilized to work done by that system. Okay, if heat absorbed by the system, then work done by the system. If heat released by the system, work is done on the system. These are the terms that you need to be clear. If this is positive, this is negative. If it is work done on the system, heat released by the system. If heat absorbed by the system, work done by the system. You can remember these statements. Okay. So, now how can we write this calculations and all? See, for this particular question, see, if you understand this concept, what they are asking, internal energy change for isothermal process. If an internal energy change for an isothermal process, how much it is? Simply no need of calculation or anything, simply you can say du is equals to 0, that option 2 is perfect. But what I am asking is, how can we calculate work done here? Okay, so you can use work done formula. We know dw is equals to minus p dv. So, for an ideal gas, we know PV equals to RT right now. So, from this you can write P is equals to RT by V also, right. So, if I say this is irreversible process, what I am saying, if it is an irreversible process, whatever the pressure they have mentioned right here, and this is final volume minus initial volume, you take, you will get your work done. Okay, whatever the work done value you will get, the same value with opposite sign will be having for heat changed, like whatever the heat changed during the process. Okay, next, if it is for reversible process, what I am saying, if it is for reversible, this is for irreversible process. Okay, and there are two more things. One is reversible or irreversible expansion or compression, irreversible expansion or compression I am saying now. So, this is in vacuum. So, in vacuum means external pressure will be P external will be 0. It means dW will be equals to minus P external dV we are writing now. If this term is 0, 0 into something 0. So, the total work done will be 0 for irreversible, isothermal irreversible expansion or expansion, free expansion into vacuum, you can say work done will be 0. If work done is 0, then its heat absorbed or released also 0, because they have same magnitude but opposite signs, that is it. So, for irreversible process, this is important. Again, for reversible process, isothermal reversible process, so I can replace dW is equals to minus P dV, right. So, P can be replaced by RT by V dV, that is it. So, dW will be now minus RT 1 by V dV. See, what I am doing is I am applying integration on both sides. See, integration of 1 by x dx will be considered as ln x right now. So, same thing I am taking here. Since if it is expansion, expands from initial volume V1 to final volume V2, and here this will be W gives minus RT ln V2 by V1. Okay, this will be the formula for work done in isothermal reversible expansion a reversible compression. You can use this for work done calculations. Okay, instead of ln you can substitute it as 2.303 RT log V2 by V1. Okay, right. Let me show you a few questions again. Look at this question. This is from IIT JAM 2019 exam, 2009 exam. It's very simple. It's very simple. See, they are saying adiabatic process. So what is this adiabatic process? First of all, adiabatic process, the conditions you need to know in order to answer this question. See, when I am saying adiabatic process, so the Q, it means amount of heat exchanged will be remains constant, I mean no exchange of heat, therefore dQ will be, change in heat will be 0. Okay, whatever the system has some heat that remains constant Q, there is no transfer of heat into the system or out of the system, that is change in heat will be 0 I am saying. So from this, using first law, du is equals to dq plus dw, no? So it means this term is becoming 0. So du equals to now dw. It means if system wants to do some work, that work done by the system can be by using its internal energy. If work is done by the system, its internal energy decreases. If work is done on the system, its internal energy increases. So in adiabatic process, if work is done by the system, cooling takes place because its internal energy is changing now, decreasing now, therefore I can say cooling takes place. Okay, right. So now again, if I want to calculate its work done, you can say then what you can say, du is equals to NCV dt. Okay, so from here I can replace this du with this NCV dt. Yes, you can directly use this formula to calculate work done by the system for n moles of a gas by looking at its CV value. Just now we calculated what is CV, Cp for different gases, if it is monoatomic gas, diatomic gas, polyatomics, linear, non-linear things we have already covered. Okay, right. Then next, if you look at this question, there are other formulas along with this for calculation of the pressure, temperature, how they change during this adiabatic process. See, you can use PV power gamma is equals to constant. Okay, or TV power gamma minus 1 is equals to constant. And one more relation here, T power T V power 1 minus gamma by gamma, that's it. So now read the question. Out of these three formulas we can use one. So tell me, identify which formula we can use for that. Which formula we can use for that? Tell me anyone. Yeah, tell me anyone here. See what to do, simply read the question once. They are saying ideal monoatomic gas. Monoatomic gas means what is the gamma value we have? I have given three gamma values. One is 1.66, this is for monoatomic gas, and for diatomic gas 1.4 I told you, and for diatomic gas or polyatomic gas with a non-linear molecule it is 1.33. So here we have monoatomic gas mentioned in the question, so you can say 1.66. The next, the gas of initial volume V0 is compressed adiabatically to V0 by 2. The initial temperature is T0 and the final temperature of the system is, see, they are saying relation between volume versus temperature right now. So volume versus temperature means you just take this is second formula. So TV power gamma minus 1 is constant. If this is constant, TV power, see what I can say, I am taking T1 V1 gamma minus 1 by T2 V2 gamma minus 1, these are constant only right now. So it means this I can relate them as T1 V1 equals to T2 V2 gamma minus 1. From this T1 by T2 will be equals to V2 by V1 power gamma minus 1 right now. So now what they are saying, initial volume is V0, this is V0, and final volume is V0 by 2, V0 by 2, V0 by 2, and gamma minus 1 is how much, 1.66 minus 1, okay, gamma minus 1 we have, so this I can write 0.66, okay. So V0 is cancelled, so here T1 by T2 we got, okay, T1 by T2 we got. So from this T2 will be written as T1 multiplied with 2 power 0.66, 2 power 0.66. So where do we have T2 is equals to T1 multiplied 2 power 0.66, our option number 6 will be perfect answer for the question. See T1, that is T1 is nothing but a T0 here they are saying, initial temperature is T0, that is what T1 I am taking here, 2 power 0.66 or 67 will be the perfect answer, that is option 4. If this is clear, use these three formulas, very important, and I am going to give you one question, the next slide, you need to answer me this one, very simple, easily you can answer if you got clarity on the previous discussion. See, look at this question here, same discussion but with the different relation, temperature versus temperature and volume pressure relation you can use here for calculating, okay. And I am saying for you the final answer you will get for this particular question will be 8, okay, this third option, okay. You just cross check if you are getting this answer, it's correct, if not you just mention in the chat box that I am going to explain there, okay. If you have any queries I will explain in the chat box for your response in the chat box, okay, right. Next, look at this, consider an equation, again it's very important relation, consider the equation given here, which are the following statements are true, which are the following statements are true. See, they are saying delta G naught is equals to delta H naught minus T delta S naught. This is the relation they have given, which is not true they are asking. See, you can expect a direct question from this relation in the exam. I am saying, for example, we are saying a chemical reaction is spontaneous. If it is spontaneous, delta G must be negative. For a spontaneous process, delta G must be negative. In order to make this negative, there are two terms, first term and second term. See, either first term has to be negative or second term has to be positive, then all term becomes complete negative right now. So if it is complete negative, then it is spontaneous, or in case if delta H is positive, then delta S should be positive with a higher value, then it will be more dominating, so the term becomes, the delta G term becomes negative, like this. Finally, what should be the conclusion here? In order to make delta G negative, what are the possible ways we can keep this? Okay, so look at the option, when delta G is negative, the reaction is called exergonic. Yes, if delta G is negative, it is exergonic. If delta H is negative, it is exothermic. Delta G is negative, exergonic. If it is positive, endergonic. Okay, and if delta H is negative, exothermic. If it is positive, if it is delta H is negative, exothermic. If it is delta H is positive, endothermic. You can remember these terms here which I used. Okay, this is correct. They are saying not correct. When delta G is negative, reaction can happen spontaneously. Yes, this is also correct. So delta S is negative. When delta S is negative, the molecular disorderness during the reaction decreases. See, S is what? Entropy. Entropy means measure of disorderness. If more is the disorderness or randomness in the system, more will be the entropy. See, generally you consider in the nature, everything in any process, in any naturally occurring process, entropy of that particular system will increases. Right now, so you consider any process, you just observe that flowing of water from hilly area to lower region, how it will splits now. It means the disorderness, the randomness of water will be increasing here. So like that, any system you consider in the nature, its entropy will be increases for its natural process. Okay, remember this. Okay, so delta S is negative, it means entropy is decreasing. So if entropy is decreasing, yes, delta S should be negative. This is also correct. They are saying delta H is negative, the reaction is endothermic. No, this is not endothermic, this should be called as exothermic. The terms which I have explained, based on that you can answer. So fourth option will be perfectly suitable answer for this question. Okay, right. Let me give you one more question. Let me show you few questions related to this. Yes, look at this question that we have solved. The relation that I have given, work done equals to NCV dt, right? So CV value is given, dt temperature change also given here, okay, and number of moles also mentioned. You just substitute in this and tell me your answer in the chat box for this particular question, because these are very easy. I hope you can easily solve them right now. So just formula substitution only, put the values and tell me your answer in the chat box for this question. Right. So the remaining things we'll discuss in the next session. Okay, so just stay connected with this CBC. Okay, and let's make our preparation more effective and let's score a better rank and let's get into a good IIT. Okay, so thanks for watching.